Okay, welcome everybody. For those of you who are in my Monday discussion section, you will have missed the first 4 problems this week. My plan here is to start with problem number 5 and go through. I think the first 3 problems are relatively straightforward. For those 3, if you need help with them, as you're going through the homework, then you can ask for, you can send me a message or whatever. And for problem number 4, I will go over it again at the end of this office hours session, because the math in that one is a little complicated. But we're going to go ahead and start today with the 5th problem on the homework as soon as I get it pulled up here. If you have any questions, you can feel free to use the chat, or yes, it will, Amber. And on that note, you can also ask questions in the comments on YouTube. And it'll be posted in the same place as last week's. Okay, so problem number 5 is our first one here. And in problem number 5, we have this projectile that's being shot through the air. And we are essentially going to have 2 different problems. So A and B, the height of the cliff and the speed of the stone before it hits the cliff, will be one problem. And then part C, which is the asked about the maximum height, will be a different calculation. So we're going to do A and B first. I could sketch the picture. I assume that most of you have it open right now. So the way that we deal with projectile motion is motion in 2 dimensions. If you did not follow or you did not have discussion this week, what I tend to do is I organize my information according to the individual dimensions, and then I try to solve each of those dimensions independently. And only when I finally exhaust those dimensions independently will I come together and link them together. So in the x dimension, since all of the acceleration here is acceleration due to gravity, that means we just have y acceleration. It would be negative 9.8. And in the x dimension, there's no acceleration. In fact, all we are concerned with then is just the displacement is equal to the velocity times the time, and it'll be a constant velocity. And so generally I start by working in the x when I'm dealing with the projectile motion problem. So our delta x, we do not know. We know that the initial speed is 49 degrees at an angle of 63. So that will be our initial velocity. We don't know the time. So the x equation will just become delta x is equal to the x component of that velocity at an angle. So that's going to be 49 times the cosine of the angle 63 degrees. And then we still have our unknown t. With 2 unknowns in this equation, so we're not going to get anything else out of it. The one thing that I will note that I reiterate over and over is that time is the quantity that is the same between the x and the y. To say that again, the time is going to link your x to your y. Okay, so let's go ahead and go over to the y side. We have our acceleration. Our initial velocity is the y component of the 49 meters per second. So that'll be 49 sine of 63. And then our final velocity we do not know. That will be our answer to part B. Our displacement in the y direction, we also don't know. This is the answer to part A, which is the height of the cliff. And then the time, again, we don't know. Now I have an equation on the left-hand side that will relate oh, I should point out here, actually, we do know the time. The time is given as 5.27 seconds. So in light of that, we can actually go ahead and plug in the time in the x equation here, and that'll give us a delta x is equal to 49 cosine of 63 times 5.27. And that will give us the displacement in the x direction, which is unfortunately not an answer that we're looking for. But anyway, we can go ahead and calculate that if you'd like to. It'll be, let's see, cosine 63 is going to be about a half, and then you have 49, so 50 and 5. Half of 50 times 5 will be roughly 125 meters. So that's a quick calculation. Again, we don't need it, but I like to say, solve it to completion if you can. All right, so for part A, they're going to ask us for the height of the cliff. For that, we'll use our acceleration, our initial velocity, and our time, which we know, and then we will solve for delta y. So we've done this before plenty of times. Now it's just a kinematics problem, and we just need, let's see, delta y. Delta y is equal to v initial t plus plus 1/2 times a t squared. Our delta y is that h that we're solving for. Our initial velocity is the sine component of the initial velocity, and that is going to be 49 sine of 63. The time, as mentioned, is 5.27. And then we add 1/2 times the acceleration. Our acceleration in the y direction is always going to be negative 9.8. And then our time is 5.27 squared. That should be a 27. And if you go ahead and plug the stuff into the calculator, you can solve for h. And given these numbers, I would get 94 meters. For part B, I'll go ahead and leave part B up to you. For part B, oops, that is more than I wanted. For part B, instead of solving for delta y, we're going to solve for v final. So we want to relate the final velocity, the initial velocity, acceleration, and time. And that will be, the equation that you use for that is final velocity is equal to initial velocity plus at. And I'll leave that calculation to you. If you have any trouble with it, just let me know. We'll go ahead and talk about part C though. As I mentioned, part C is going to be a different calculation. In part C, you're asked to find the maximum height. So whenever we're finding max height, that's a keyword that gives us one of our quantities. The maximum height is the height at which the object turns around. So it's going to go up, it's going to hit the maximum height, and then it's going to come back down. When it's going up, the y component of the velocity is positive. That's why it's traveling upward. When it's coming down, the y component of the velocity is negative. That's why it's coming downward, which means that at the max height, our velocity in the y direction is going to be 0. So in light of this, we can sketch out our problem once again, organize our information by x and y. On the x side, we'll have the same constant velocity equation, delta x is equal to velocity times time. In this part of the problem, we do not know the time. We're not given the time. So our equation here will be that delta x equals, was it 49 cosine of 63 times the time. On the y side now, our givens are going to look a little different. So our acceleration is still, as always, negative 9.8 in the y direction. I don't know what I was doing there. Negative 9.8. Our initial velocity is going to be the same, the sine component of the initial velocity, 49 sine of 63. The final velocity, here is where our keyword max height comes in. The final velocity in the y direction is 0 if we're trying to investigate the point at the max height. And then we have enough information here to find either delta y or find the time. In this case, they simply ask for the maximum height itself. That maximum height is going to be our delta y. So we'll pick out the equation that's going to relate the acceleration, the initial velocity, the final velocity, and our displacement. And that is going to be v final squared is equal to v initial squared plus 2a delta y. Our final velocity is 0. Our initial velocity is our sine component, 49 sine of 63. That quantity will be squared. Then we have plus 2 times negative 9.8 times delta y. And if you solve this guy for delta y, you'll get that delta y is equal to, with my numbers, 97.3 meters. Any questions on this one? Got a negative for part B. So the reason why, that's a really good question, Amber. The reason why you get a negative for part B is because the y component of the velocity is going to be downward. So that is a negative velocity. Now they ask for the speed of the stone. The speed of the stone, remember, is the magnitude of the velocity. The last note that I'll make for part B is that when you find the y component of the velocity, you need to add it in quadrature. So what I mean there is that your final velocity will be equal to the square root of the x velocity squared. The x velocity is constant, so that'll be, for my numbers, 49 cos 63, I think is what I had. And then you'll do plus vy squared, where this is the final velocity that you find using the kinematic equation. So this will give you the magnitude. You could put it like that. That'll give you the magnitude of the final velocity, which is the speed, and that's what part B is looking for.
Oh wait, so is part B asking for like the full-on like complete velocity, not just the x or y component once it put together?
All right, problem number 6. In problem number 6, we get a particle that's going to start from the origin. They give us a velocity in the j hat. We're going to move with a constant acceleration. And then and that acceleration is both I hat and j hat. So in other words, the velocity has a y component. The acceleration has both x and y. They ask us at the instant that the particle's x coordinate, and they'll give you an x coordinate. Then they want to find the y coordinate and the speed. And since we start from the origin, our initial x position, our initial y position are both going to be 0, which means that delta x and delta y will just be equal to those coordinates. I'm going to write that explicitly in just a second, but I'm just going to make a note. But I'm going to go ahead and solve this as I always do. Start by organizing my information into the 2 dimensions, separate those dimensions out. In this case, we do have an acceleration in the x direction. So our acceleration is the I hat component of the acceleration that's given there, 4.8. Our initial velocity in the y direction, I just want to take a second to note this. We're given a velocity as mine is 5.3 j hat. There is no I hat component on that velocity. If there is no I hat, then that means that the x component is equal to 0. It's like having a 0 I hat plus. So our initial velocity in the x dimension is 0. The final velocity, we don't know, but we will need to find that in part B. The displacement in the x, as I mentioned, our initial x position is 0 since we start at the origin, which means that our delta x will just be equal to whatever that final x position is, which is given here as 29. And then the time, we don't know. but that time will be our link between the x and the y. So right here, you might go ahead and say, yes, my time will link my x to my y, so I'm going to want to calculate that at some point. If that doesn't jump right out to you, then you can move over to the y side. Our acceleration in the y direction is 1.8. Our initial velocity is that j hat component of the velocity that's given, 5.3. Our final velocity in the y direction, we also don't know. We will also need to find that final velocity for part B. The delta y, as I mentioned, we start at the origin, so delta y is just equal to y final. And in that case, in this case, y final is what we're trying to solve for. The time, again, we do not know. Now the problem becomes a little bit clearer. We have acceleration and initial velocity. We have two quantities known in the y direction. We need to find a y final, which means we need either final velocity or time. But remember that the thing that links the x and the y together is going to be the time. So the most useful information that we can get from the x side is going to be the time. And so we pick the equation that relates acceleration, initial velocity, and delta x are three known quantities to the time. And that will be the equation v final equals v initial plus a t. I'm sorry, we're relating delta x initial velocity, acceleration, and time. So that's delta x equals initial velocity times time plus a half a t squared. Our delta x is 29. Our initial velocity is 0, so this first term goes to 0. And then we have a half times the acceleration, which is 4.8, times the time squared. And that'll be roughly, what is that? 30 on 5 gives you 6 times 2 is 12, and then the square root of that. This will be something like 3.4 seconds or so. Brian, the acceleration here is given in the problem for number 6. They tell you it has a constant acceleration, and then they give you some number I hat plus j hat meters per second squared. So that acceleration is just given. All right, once we have our time, and the time is the same for the x and the y, right? Because the object is moving through both dimensions at the same time. Now we can go ahead and find the equation that's going to link acceleration, initial velocity, delta y, and time. It's actually going to be the same equation that we just used. We'll just do it again. And we'll have delta y is equal to initial velocity times time plus 1/2 at squared. And as I mentioned, as I have written down there, delta y is equal to y final, so we can go ahead and do that sub. That's going to be equal to 5.3 times time. Oh, sorry, I know the time now is 3.4 plus 1/2 times the acceleration, which is 1.8 times, running out of room here, 3.4 squared. It's not going to want to let me do that. 3.4 squared y. That should all be in one line. If you want to put that all in one line in your notes so that you know what you're looking at. Someone's going to ask me what's going on there, but that's all multiplied together. 1/2 times 1.8 times 3.4 squared. And if you plug that into your calculator using these numbers, you should get a y final of 29.3. Now for part B, the way that I would solve this, I'm going to need to find the speed, which, as we just mentioned, the speed is the magnitude of the velocity, which will be equal to the square root of the x component of the velocity squared plus the y component squared. Yes, James, yeah, make sure you're always in degrees mode in this when you're doing physics. Okay, so yeah, so we need to find both the x and the y. The one note that I'll make when solving the x, this is just how I do it. You now have the time, so you could plug the time in as well. But for me, I'd say, since I was given in the problem acceleration, initial velocity, and the delta x, I would pick the equation that has those three and final velocity. But that's just to make sure that we don't lose value to rounding. So I'm just going to write down which equations I would choose for each dimension. So for the x, I would use the v final squared equals v initial squared plus 2a delta x. And then for the y side, I'm going to have to use either the time or the y final. Since I found the time first, that one has the least rounding, so I'd choose to use that one. I would use time, initial velocity, acceleration, and final velocity. So the equation that I would choose to use, but there's, again, not necessarily a wrong answer. This just cuts down on your chance of having an error, is v final equals v initial plus at. Do you have any questions here? Okay, don't see anything going on there. Go ahead and move to problem number 7. Problem number 7, you've got a women's volleyball net. So for v final for both and square. Yes, yeah, Amber. So that's, you're adding in quadrature. So that's this green equation that I put right here. Once you find your final velocities from these two equations, then you go ahead and plug them in here, square, take the square root. And that's how you'll always find speed if you're dealing with multiple dimensions. And that's a way that they ask you to solve for both, essentially. Okay, so we have a women's volleyball net, and they tell us the height of the net above the floor, and they tell us the measurements of the court. Player's going to jump and hit the ball at a point, a certain height off the ground. You'll notice that that point is higher than the net. So I'm going to draw a very, very rough looking net here. The height of the net is, it'll be different for everybody. The height of my net is 2.24. The serve is being hit from a higher height. I believe this will be different for everyone else as well. Mine is being hit from 3 meters. And crucially, the problem says the initial velocity of the ball is horizontal. So if the initial velocity is all horizontal, what that means is that our initial velocity is equal to just the x velocity. In other words, our initial velocity in the y direction will be equal to 0. All of the initial velocity is in the x direction. That's what it means to strike something horizontally. And then the path that the ball would take would be something like this. So it's going to come down because of gravity. But what they're going to ask us for is the minimum magnitude it has to have to clear the net. In other words, what's the softest that you could serve the ball such that it will still be able to clear the net. You don't want the ball to hit the net, obviously, right? So if they're asking for the magnitude of the initial velocity, that's going to be our initial velocity, which is all, again, all in the x direction. So for part A, I would, again, just organize my information by x and y. Now we are again in projectile motion. There's no acceleration in the x dimension in this problem. So our x just goes back to delta x equals velocity times time. And they give us delta x. They tell us that the player is 8 meters from the net. It'll be different for everybody. So delta x will be 8. We don't know that v, but that is the velocity that we're solving for. We also don't know the time. So we have to go to the y side. Our acceleration in the y, as always, negative 9.8, the acceleration due to gravity. Our initial velocity in the y direction, I wrote it down over here, it's 0. Our final velocity in the y direction, we don't know. Our delta y. Our delta y, keep in mind, final position minus initial position. Our final position, if we're just going to clear the net, would be the height of the net, 2.24. And our initial is at 3. So you can do 2.24 minus 3, and that'll give you negative 0.76. And then finally, we do not know time, but you'll notice that we have 3 quantities in the y direction, and you'll notice that we want the time. And remember that our time is the same in both dimensions. So if we can solve for the time for y, then we can solve for the velocity in x and solve the problem. So knowing acceleration, initial velocity, and delta y, and looking for the time, we go back to the old trusty, nope, I don't want to use the highlighter. Delta y equals v initial t plus 1/2 at squared. And I'll answer your question in just a second, Alexa. Delta y is negative 0.76. The initial velocity is 0, so our first term goes to 0, and then we have plus 1/2 times negative 9.8 times t squared. And let's see, so multiplies, that'll be about 1.5 on 10, so 0.15. The square root of that will be something like, what's the square root of 0.15? It'll be something like 0.45 seconds or something. That's close enough for us. And then the last step here is to go back to our x equation, which was 8 is equal to velocity times time. Solving that for velocity, velocity is equal to 8 over the time, which is 8 over that 0.45, which will give us something like, oh, actually no, 20.3. And since this is a velocity, our units are going to be meters per second. Okay, so Alexa asked again, just to clarify, right? Asked why delta y is negative. So I kind of did the calculation a little bit in my head, but just to go through that calculation explicitly, delta y, let me get the eraser here. Delta y is equal to y final minus y initial. Our y final is the height of the net. That's 2.24. and our y initial is the height from which the ball is struck, which is 3. So if you do 2.24 minus 3, then you'll get a negative 0.76. Another way of explaining why that delta y is negative is because the ball is being pulled downward, so it's going to be displaced down in the negative y direction. And so you should end up with a negative displacement. Cool. Any other questions on part A? All right, for part B, they asked what the maximum magnitude is that the ball can have of the velocity of the ball, such that it hits inside the back line on the other side of the net. All right, so we have as I mentioned before, the ball is hit 3 meters above the ground. There's our net. It's hit something like 8 meters from the net. They also tell us that the court measures 9 by 9 on each side, which means that the out of bounds line on the other side will be 9 meters away from the net. And they want to know essentially, like, if you hit it, obviously if you hit the ball too hard in volleyball, then the ball is going to fly out of bounds. So what is the hardest that you could possibly hit it that it would stay in bounds and you'd still get the point? So in that case, what we'll be looking at now, we're not going to be necessarily concerned with the net. We know how hard we hit in part A is enough to get it over the net. Now it's definitely going to clear the net, but the question is how hard can we hit it and it still lands in bounds? So the ball will travel something like this, and it's going to land over here on the right-hand side. And it's just essentially another projectile motion problem. Organize our information here into x and y. On the x side, this is the one little bit of intuition that we need to access ourselves. The delta x, if it's traveling 8 meters to the net and then 9 meters past the net, that'll be 8 plus 9, which will give us 17. And then we can go ahead and plug that into our constant velocity equation. Delta x is equal to velocity times time, and we'll have 17 is equal to whatever that initial velocity is, which is still what we're solving for in this section, in this part of the problem, and then times time, which again we don't know. So once more, if you're starting to see a pattern here, if we need the time for the x, we have to go to the y. If we need the time for the y, we have to go to the x. Time links x to y. So go ahead and go over to the y side. Acceleration is negative 9.8. Your initial velocity is still 0. The ball is still being struck horizontally. The final velocity we don't know, and we're not asked to find it, so we're probably not going to deal with it. Delta y changes a little bit here. And the last problem, we were just going from where the ball was hit to the top of the net. Now we're going from where the ball is hit all the way down to the floor. Now just to do, since we had some question, just to do this calculation explicitly, that'll be y final minus y initial. Y final is the ground. I personally always set y final to be, or rather the ground to be 0. So if the ball ends up on the ground, it ends up at y equals 0. It starts off 3 meters above the ground, so that'll be minus 3. And that's where we get our negative 3 for delta y. We do not know the time, but as I've mentioned, the time is going to be the quantity that we carry over to the x. We do know acceleration, initial velocity, and delta y. I'm going to leave the problem solving to you from here, but I will tell you that you want to use delta y is equal to initial velocity times time plus 1/2 at squared. Once you do that, you'll solve for time. And then you can plug the time into our 17 equals velocity times time. And you'll solve for the velocity, which will be your answer. And it should be larger than the answer to part A. So if you're getting smaller, then that's a good sign that you maybe missed some calculator work. Do you have any questions on this problem? Oh, I just realized that my sound isn't on, so if anyone's been talking, I have not heard you, and that's my bad. I don't think anyone's been asking questions, so. Okay. Yeah, the next problem. All right, now we're getting into conceptual territory a little bit with this problem. So those of you who were chugging through the first set, what are the units for 7b? If you're solving for a velocity, your velocity is almost always going to be meters per second in this class. Yep. Okay, so question number 8. We have a particle traveling along a straight path through x and y. It's accelerated from rest. So if it's from rest, that means that your initial velocity vector is 0, which means both your x and your y components are 0. You don't need to write that down if what I said makes sense to you. And it's going to move from point A to point B over some time interval, delta t1. The acceleration is constant. The xy coordinates are given. Those will be different for everybody. Given for point A and given for point B. What they ask us for is not to solve for a number. Now they're asking us to find the ratio of the accelerations. And you could intuition your way through this. Some people may be able to do that. I'm going to show how to solve it if you are looking at it like I have no intuition how to do this. I'm going to show how to solve it, and then we can talk a little bit about the intuition at the end. So just as we've always done, start by organizing our information into x and y. In the x direction, we're going to have some acceleration. We don't know what it is, but they refer to it in the problem as a sub x. So maybe we'll go ahead and call it a sub x. Our initial velocity, as I wrote down at the top of the screen here, is 0. Our final velocity, we do not know. Our delta x, which is x final minus x initial, will be the x at the point B minus x at the point A. So my bx is 10 and my ax is 3.3. 10 minus 3.3, or sorry, 11. I guess it doesn't much matter. 11 minus 3.3, which is going to be, what's that, 7.7? And then I do not have a time. They do tell me that the time interval is called delta t1, so I'll go ahead and use that. Right off the bat, you'll see we have a lot of symbols, but we only have 2 known quantities. We only know initial velocity and delta x, so we don't have enough to like directly solve for anything just yet. So I just continue to organize my information. I go over to the y side. My acceleration on the y side is going to be a sub y. That's just what it's called in the problem. My initial velocity in the y side is also 0. My final velocity is also unknown. The way I calculate delta y, the same way I calculated delta x, will be the y component of b minus the x component of b. For me, that happens to be 15 minus 6.9, which is 8.1. And then the time, keep in mind the time's going to be the same for both. The time interval here is delta t1. All right, so this is much more symbolic than the problems that we've done so far. We're also not solving for a single quantity. Oh, this should not have said v final is 0. This should have said v final is unknown. So we're not able to solve for a quantity anyway. What we do know is we know that delta t1, our time interval, is the same for x and y. And we know that we want to ultimately find a ratio of a sub y to a sub x. So my intuition tells me let's take the quantities that we do know, and let's also use our accelerations since we want those in our answer, and let's use time. So on the x side, we're taking a look at this since the known quantities are the same in both. So for both of them, we're going to use the same equation. Acceleration, initial velocity, delta x, and time, which will be displacement, is equal to initial velocity times time plus 1/2 at squared. And, or delta y or delta x. So I'll just write down, we're going to use the same equation for both. For the x, what we get is 7.7 equals, the initial velocity is 0, so our first term is going to go to 0 in both the x and the y. And so we just have 1/2 times our acceleration, which we've called a sub x, times the time, which is delta t1 squared. And for the y, we're going to have a very similar equation. The only difference is going to be our delta y is a little bit different. My delta y is 8.1, and that'll be equal to 1/2 times a sub y times delta t1 squared. So I have these two equations with two unknowns each. I could solve, do a substitution maybe. I have delta t1 in each of them, so you could do delta t1. Another way to go about this, the way that I would do it, maybe it's a little bit more elegant. If I want to find a sub y over a sub x, what I can simply do is divide my y equation by my x equation. Here's what that would look like. On the left-hand side, you just divide 8.1 by 7.7. I'm going to have to do this on the next page because I'm running out of room. So we have 8.1 divided by 7.7. On the right-hand side, we're going to divide the right-hand sides of the equation. So we'll divide 1/2 a sub y times t squared over 1/2 a sub x times t squared. I'm going to get some questions, I'm sure, about why I decided to divide the y equation by the x equation, not the other way around. The reason is because ultimately we want a sub y over a sub x. So once I cancel out the common stuff on the right-hand side, then I have a sub y on a sub x is equal to 8.1 on 7.7. You could divide the other equations. Like I said, you could do substitution as well. You'll get to the same answer no matter what. And this will give us 1.05. What are the units for a ratio? If I have meters per second squared divided by meters per second squared, the units will cancel out there. We don't have units, in other words. For part B and C, the second part of the problem, they're going to ask us for the x and y coordinates of the particle if the motion is continued for another interval equal to delta t1. Oh yeah, thank you, Michael. Yeah, so how would we get there just from intuition? The way that I would get there from intuition is to take a look at this blue equation in the upper right-hand corner, the delta y equals initial velocity times time plus a half at squared. And what I would see is, given that our initial velocity is 0, I'd see that the time is squared, but the acceleration is proportional since this first term goes to 0. This is the intuition explanation, everybody, so don't worry about it if you're good with the math. That first term goes to 0, and so what we end up having is delta y is proportional, or delta x will be proportional to the acceleration in the y or the x. And so then it's just straightforward to say that means that the ratio of the accelerations, a sub y on a sub x, would be the same as the ratio of the displacements, delta y over delta x. Yeah. So that's essentially the math that I did kind of prove that out, Michael. But yeah, you could just write down that answer with the intuition, but you can definitely run astray if you rely on intuition too heavily. Like in part B, you could do some intuition for part B and see. I would recommend against it. I would recommend just doing things the old-fashioned way, which is to say organize our information by x and y. The acceleration in the x direction will still be a sub x. We haven't changed that. Our initial velocity is still going to be 0. Our final velocity is still unknown. Now we need to find a delta x. They're asking us how far it would travel, given that it travels for another length of delta t1. So that means that the time in this problem, if we're traveling for twice as much time, it would be 2 times delta t1. Go over to the y side. The acceleration is going to be a sub y. Our initial velocity is still 0. Our final velocity is still unknown. Our delta y now is the thing that we are after as well. And our time, the same as it is on the x, is 2 times delta t1. The equations are going to be the same. We are again going to use the delta x or delta y is equal to v initial t plus 1/2 at squared. For the x equation, our delta x is unknown now. That's the answer that we're looking for. Our initial velocity is still 0 for both x and y, so that first term will go to 0 for both of them. So we just have delta x is equal to 1/2 a sub x times 2 delta t1 squared. And for the y equation, we have delta y is equal to 1/2 times a sub y times 2 delta t1 squareds. Now, there's intuition that can be used to solve from here. You'll notice that we doubled the time, but since that's squared, that means that you multiply the right side of the equation by 4. In other words, if you double the time, then you will increase the displacement by 4 times. So that's your intuition, if you're comfortable with that. And I believe like the solution that they will give you once they post them is going to say something to that effect. For myself personally, what I'm trying to see here is if there's a way, if we just like don't even pick up on that intuition, if there's a way to get to the solution mathematically. And I think it's just going to take a little bit of comparison. So yeah, so I think what we have to do is we're going to have to inspect our equation from part A. So the delta x from part A was equal to 1/2 times a sub x times 2 delta t1 squared, times just 2, no, it's just, can't write and think at the same time. It's just 1 delta 1 squared. So this is our equation, from, where were we back here? One more slide. This was our x equation right here that we found. Our delta x was 7.7, yours will be different. But the point is that the displacement from part A is proportional to 1/2 a sub x delta t1 squared. Now we have this new equation for part B that will relate our new displacement to 1/2 times a sub x times 2 delta t1 squared. And I know the delta x from part A. So if I can isolate this set of variables, 1/2 a sub x delta t1 squared, from the right-hand side of my second equation, then I could just plug in my displacement from part A, and I'd have a relationship to the displacement for part B. So in order to do that, all I need to do is pull out the 2 from inside the parentheses, but keep in mind we need to square it. So we have 4 times 1/2 a sub x times delta t1 squared. And since the stuff that's inside the parentheses is equal to the delta x from part A, that means that our delta x from part B will be 4 times the delta x from part A. From here then, you just plug in, find your delta x, and go back to the coordinates and use the displacement delta x is equal to x initial, x final minus x initial. Some people are going to need help with that. That's fine. Some of you will be able to get that. If you do need help solving that, then let me know. One thing that I will note is that the argument for the y direction is the same. So just as delta x in part B is 4 times delta x in part A, delta y in part B will be equal to 4 times delta y in part A. You got lost after I pulled out the, yeah, so what we've done here, Nina, is we've expressed both the displacement for part A and the displacement for part B in terms of the same variables. So I can do a substitution where if I can solve for the set, or the term on the right-hand side of the top equation in the bottom equation, then I can just substitute in delta xa. So I'm very close to start. The only difference between the two is this 2 that's on the inside. So I square it and pull it out. And then what I'm left with is this term right here. And this term, 1/2 a sub x times delta t1 squared, I know from the first equation is just equal to delta xa. So it's just a substitution like in algebra. But now we're substituting out a ton of variables for just one, which is why it looks a little bit wonky. There's probably other ways to do that algebra. Unfortunately, because we don't have numbers, we do need to somehow relate our displacement in part B to our displacement in part A. The intuition that we gain from this problem is that when you double the time that a constant acceleration is applied, you increase the displacement by 4. Can you find the slope of the line and use that to find x? Whoa, okay, a lot of questions. We multiply our delta x and delta y by 4. Amber, yeah, so that's, again, so since we doubled the time and time is squared, we would increase the displacement by 4 relative to part A. Michael asks, can you find the slope of the line and use that to find x, y? If you find the slope of the line, since we are, the slope of the line will give you roughly, give you information about the direction that you're going, but it won't tell you how far you need to go. So you do need to be able to do the physics, which tells you that by traveling for twice as long with a constant acceleration, that we would travel 4 times the distance. Cool, looks like everybody's kind of on the same page. Don't feel too bad if you're not, if this isn't immediately making a ton of sense to you. This is a little bit of a higher level problem because we're not dealing directly with numbers and we're doing a little bit more symbolically. All right, I need to clear these out.
So is the final answer for this question given in like just
All right,
like delta x?
our next problem. Yeah, so we have a balloon here. Oh, is someone asking a question? Let me see if, I don't know why I'm not hearing audio. Let me check the microphone, headphones. Okay, Brian, you can go ahead if you can hear me.
Oh, yes. Sorry, I was just wondering. So is 8 given, like the answer is all given in terms of like that delta xa since we don't know what it is?
We do know the delta xa, so we
Oh.
calculated the delta xa by
at the
taking,
very beginning.
yeah.
Part A, right?
Yeah, so since we have a number for delta xa, that's why we want to try to figure out the relationship between delta xb and delta xa.
Oh, okay. All right. Thank you.
Yeah, no problem.
I had a quick question as well.
Yeah, go ahead.
So I got like delta xa is equal to 8, and so like besides multiplying it by 4, like obviously that would give me 32. But like, what other calculation do I need to do to find the x coordinate?
Yeah, so once you do that, you'll have, that will be your delta x. What you need to find is x final. So you do delta x is equal to x final minus x initial. Plug in the x coordinate for part A. That will be your x initial. And then you solve. So you'd have delta x for part B. Here, let's do this. Let's just go back to the definition. Delta x is equal to x final minus x initial. Therefore, the delta x for part B will be equal to...
Oh, okay. So is x initial just the first value of A?
Yes.
Okay. Thank you.
Yep. Do you have any other questions?
And then we basically just do the same thing for y.
Yeah, it's identical for y.
Okay.
Thank you, everyone who gave me a heads up about the microphone question. Okay, so in the next problem, this is going to look a little bit different than anything we've done. We have a balloon that's drifting north and east and upward in some time. And we want to find the magnitude of the average velocity and the angle that velocity makes with the horizontal. So Jonathan, they'll be on YouTube. I can show you how to access that after if you want to stick around for a second. Okay, so part A, they asked us to find the magnitude of the average velocity. I guess the difference here is that we're traveling in 3 dimensions. I think everything we've done so far has only been in 2 dimensions. So we're just like barely dipping our toe into some 3-dimensional motion. And luckily the motion is very simple. We have a balloon that's just drifting and they're just asking us to find average velocity. Unfortunately, we don't have like an X, Y, and Z, but you can sort of make up your own if you're comfortable with that. So what I would typically do, let's see, your intuition is going to be to have Y as the, you're never going to, Okay, so for this problem, what I'm going to do is I've got never eat soggy waffles. That's the most challenging part for me, is remembering how those go. And then we're also going to have like upward, which is out of the screen. But what I would do is I would just relate these to positive x, positive y. So a northward motion, that's supposed to be a y, not a very great y. But a northward motion would be in the positive y, and an eastward motion would be in the positive x, and then an upward motion would be in the z. So point here is that I can do the same thing that I've done where I organize by dimension. but now I'm going to do x, y, and z. And they asked me to find the average velocity. And I know the equation for the average velocity is average velocity is just equal to delta x divided by the time, or delta t, just to be precise. And I need to find it for all three of the dimensions. I think that this part will be pretty, I hope, pretty straightforward for everybody. One thing that I'll point out is that the delta t for all three of them is going to be, in my case, I have 3.9 hours. Point is that you're going to be given your time in hours. And in the units, I don't think I can see what the units will ultimately be given in. So I'm not sure if you're given meters per second as a possible units. I would think that they probably wouldn't give you that because that would be confusing. This is one of the very, very rare cases, this problem, where we're not going to convert to meters and you're not going to convert to seconds. So maybe I shouldn't explicitly give you the units for part A, but whatever. Make sure that your units for part A are in kilometers per hour. And then you don't need to convert anything. So I'm just telling you now, you don't need to convert anything for part A. As we're finding the average velocities here, our delta x will be the eastward component, just because I've chosen that. So that'll be like, for me, it's 7.8 kilometers over my 3.9 hours. My delta y would be the northward component. So I guess I should just write that, huh? How about we say that the x is east, the y is north, and the z is upward. Rather than writing out the calculations, because everybody's numbers are different. So that's how I do it. I'd relate the three dimensions this way. The one thing that I do want to note is when you are finding the magnitude of the average velocity, excuse me, in other words, what we were finding there is we're looking for the total magnitude in all three dimensions. So the magnitude of that velocity, we've done a lot of x squared plus y squared and take the square root. In this case, we'll do the velocity in the x direction squared plus the velocity in the y direction squared plus the velocity in the z direction squared. Again, not going to give direct solution here, but I'm confident that everyone can do that calculation there. Now, the more complicated part, and I think the part that, if anyone's attempted this problem, probably the part that they're struggling with, is in part B, we're asked to find the angle that that velocity makes with the horizontal. So the horizontal, this is really poorly defined. I do not like this question or the way that they use the word horizontal. I typically take horizontal to mean off the positive x-axis. The horizontal here, what they mean is that the horizontal is the ground. So you want to find the angle. Let's do, how about we make ground green? Your balloon is going to travel upwards into the sky and shrink for some reason. And as it does so, it's going to be displaced some distance along the ground. We know the height. This is what we've defined as the z component of the height. Ultimately, we want to find the angle with the ground, not just the angle with, say, the eastward direction or the northward direction. We want to find the angle with the ground. So you'll notice here I do have a right triangle, which is nice. But the issue here is that I don't have a direct relationship to this distance here. I actually don't know what that distance is. So if I take a look at like a bird's eye view, of the same situation, what's going to happen looking down at the ground if the right is east and upward is north, the balloon, as it's rising, as we've shown in part A, is going to move some distance northeastward, not perfectly northeastward, but it'll move some distance northeastward. And the point here is that this length here, this hypotenuse in the northeast quadrant system, is going to become the leg of this triangle. So we know that that hypotenuse is as we've defined it, will be theta is equal to the arctangent of y over x. And for this, you don't need to use the velocities. You can just use the distances that are given. And the y, as we defined it, it will be the northward component, and the x would be the eastward component. Why am I finding the angle? I'm sorry, I'm running out of coffee here. That I could find the angle if I wanted to. I don't want to find the angle. What I want to find is the actual length of that. That's going to be a hypotenuse, so that calculation is even easier. So call it whatever you want. You could call it, I guess we'll use r. It's one that we're comfortable using. So r will be equal to the square root of x squared plus y squared. And just to give you some symbols that you can look back at later, that would be our displacement in the eastward direction squared plus our displacement in the northward direction squared. So this r is the same as this r along the ground. Once we calculate that r, we can go ahead and find the theta. And here's where we'll use theta is the inverse tangent of the opposite over the adjacent. Which will be the inverse tangent of z over r. And if you're taking notes and you'd like to, you could have one more line where you plug in right here. Do we have any questions on this one? This one's not too physically challenging. The challenge here is spatial and moving through 3 dimensions comfortably. Okay, Nina, so why are we doing z over r? We're trying to find the angle that the balloon's path. So this is the balloon's path right here. The hypotenuse of this other right triangle. We essentially have 2 different right triangles. We have a right triangle when we're in a bird's eye view, which is this right triangle here. And then we also have the right triangle when we're standing on the ground looking parallel. And that's this right triangle right here. So ultimately, the problem asks us for the angle that the balloon makes off of the ground. So we need to relate that back to the dimensions that we have. We know that z is going to be opposite to that angle of elevation. And we know that the r, as calculated in the right-hand side, will be the adjacent side of our right triangle along the ground. So when we do opposite over adjacent, just going back to the definition of tangent, tangent is equal to the opposite over the adjacent. The opposite from this angle is z. The adjacent to it is that r, which is the resultant between x and y. Yes, Jonathan got it. So r is the hypotenuse of the 2D triangle for x and y. And it happens to be the adjacent of the triangle for the 3D view. Yes, that's correct. And this is, again, why I really detest that they're like asking for the angle of elevation off of the ground and they're using the term horizontal. I think that that is where the point of confusion comes in here. This is not, this problem and the way that we've done this, the way we've talked about it, is not going to lead anywhere in this class, I don't think. I don't think this is ever going to come up. When we do deal with 3 dimensions, we'll very strictly stick to X, Y, and Z. You want to do the Pythagorean on the velocities, Nina? The higher level answer to your question is that you could do the Pythagorean on the distances, and then you could just divide that by time to find the average velocity. And that would be a way to check your answer to make sure you're doing it correctly if you have it on a quiz or something. Cool. All right. Oh, steps to find Z and R again. Yeah, so Z is given to you in the problem, Michael. That would be the upward motion. And we also have the, as we've defined it, X is the east and Y is the north. So we have X, Y, and Z given. The way we find R is because we want to find the distance that the balloon travels relative to the ground, right? That's what this is. This is like the projection of the balloon's path along the ground. That's our R. So in order to find that distance, we have to do the X component and the Y component of the distances added in quadrature. Okay. All right, so go ahead and do part 10 here as well. Problem 10. Problem 10, we throw a dart horizontally. We now know what horizontal means. Horizontally means that the initial velocity is all in the X direction, and there's no initial Y velocity. We're given the initial speed is 11 meters per second, and it's thrown toward a point P, which happens to be the bullseye. So you throw a dart toward the bullseye, you throw it directly at the bullseye, but it's going to hit lower, right? If you try to aim for a bullseye, the gravity is going to pull the dart down, and it's going to land on the bottom, or, you know, toward the bottom of the dartboard. That's what's going on. And they give us a time. They ask us for the distance PQ. So we can draw a picture. Here's our dart. It's going to look like a missile. And here is our dartboard. I'm going to aim the dart directly at the bullseye. And that's our point P. But because gravity is going to pull the dart downward, it's going to travel like this. And it's going to hit some point below the center of the dartboard. And that point is called Q. And they're ultimately asking us to find the distance from P to Q. This is a little bit of a convoluted way of asking us for something that we already know. We are in projectile motion, once again, back to where we started from. So we can do the typical organization here, X and Y. There's no acceleration in the X direction, so we just have delta X is equal to velocity times time. We know the initial speed is 11 meters per second. We know that initial speed is all in the X direction. So that will be initial speed of 11. And we're also given the time. My time is 0.19. So it'll be 0. Oh, that'll be some distance. 19, something, 20, 2, something like 2 meters. You'll notice here we're looking for the distance PQ. That PQ is a vertical distance. It's not related to delta X. So we found delta X, but that's not part A. That is, however, part B. They ask how far away from the dartboard the dart is released. Oh, hey, that's going to be part B. So we just kind of accidentally stumbled upon that just by solving the problem. We still need to solve for part A, so we go to the Y side. Our acceleration in the Y, as always, is negative 9.8. Our initial velocity in the Y direction is 0 because our initial velocity was all in the x direction. It was horizontal. Our final velocity, we don't know. Our delta y, all right, so delta y is going to be the displacement. That will be somehow related to the distance p to q. Since they're asking us for an exact distance, it's not going to be an exact relationship. In other words, it's going to be off by a negative sign. But what we can say with fairly certainly is that we do want to solve for that delta y. The time is, again, given minus 0.19. And I see right here that I have enough to solve. I just pick the old reliable equation. And that's going to be delta y is equal to v initial t plus 1/2 at squared. We don't know delta y, but we know everything else. V initial t is going to go to 0 because there's no initial velocity. So we just have a half times negative 9.8 times the time, 0.19 squared. And this will give us delta y. Now this is going to give us a negative. It'll give us negative 0.18 meters. The negative indicates that it is downward distance. However, since they're just asking us for a distance from P to Q, that distance PQ will just be the magnitude of delta y, which for me is just 0.18 meters. All right, do we have any questions on this one? If not, if you came to discussion, then you have now been through all the problems and you're good to go. I'm going to go ahead and go back, as I mentioned, I'm going to go back to number 4. Yeah, let's see if there are any other questions. So Michael just asked about 6b. Yeah, do you want to go ahead and ask Michael? Excuse me.
Yeah, sure. So I know you're supposed to calculate v final for both like the x component and the y component, but when I was calculating it for the x component, I got a negative when I was trying to do the square root. So the way I set it up and the way that we set it up is v final squared is equal to v initial squared plus 2a delta x. And then I basically just plugged in the values for the initial. So I got like 2 times negative 9.8 times delta x, which was 29, which gave me like a negative answer, obviously, because there's only one negative on the right side. So then when I tried to find the square root to solve for v final in the x component, I couldn't get an answer because it was like taking the square root of the negative.
Yeah, run me through again. What was the negative in the right side of your equation? It was the acceleration?
The acceleration.
So you have a negative on your I hat, you have a negative there? For question 6.
Wait.
There's a different one.
Oh, okay. No. I just plugged in negative 9.8 because I was just rushing through it. Okay.
Yeah.
So I should use 3.6. Okay, so 3.6 sounds about right.
Yeah, whatever it'll be different for everybody, but yeah, I think everyone's accelerations should both be positive there.
Okay, and then the same thing for y. I was gonna make the same mistake, and so and then I just use j hat.
Yep. So yeah, we gotta be careful about differentiating. You'd only use negative 9.8 in the y when you have a projectile.
Okay, and then once I find both of the v finals, then I just do the square root of the sum of their squares.
Yep.
Okay.
Yep, you got it.
Thank you.
Yep. Okay. I'm gonna go ahead and talk about problem 4. Just because the math here gets a little wonky, so I at least want to give everyone a fighting chance at solving this problem. Now I have 2 particles. I have a particle B with one acceleration given, and I have a particle A. Particle A is a little bit of a nicer particle because there's no acceleration, and we have a constant velocity that's all in the x direction. So particle A's motion is pretty easy to describe as an equation. And ultimately what we want to solve for is we want to solve for the motion required to get these two particles to collide at that point that I've drawn there. So as I mentioned, particle A is pretty straightforward. Maybe you'd start with particle A, maybe you wouldn't. Particle A only has x motion, and it's constant velocity, so it's just delta x equals velocity times time. I do not know the delta x, but I do know the velocity. For me, my magnitude, my velocity is 3. So I might call it delta x is equal to 3 times time. I could go one step further right here, but I think I'm going to leave this right where it's at, and I'll come back to it. This is an equation that we're going to use in just a second. What we need to do next is we need to deal with particle B's motion. Particle B has an acceleration that's given, just the magnitude, and that acceleration is at an angle, so it's going to have an x and y component. Now, in order to get through dealing with particle B, I go back to the tool that I have, which is to discuss the x and y directions independently. We're going to have acceleration in both directions because our acceleration is at an angle. The acceleration for the x direction will be the magnitude that's given, mine is 0.42. Since they want the angle off of the vertical, the x component is going to be the sine component, which is a little strange, a little different than how I've done it before. My initial velocity in the x direction and in the y direction for B, since it starts from rest, is 0. My final velocity, I don't know, and I'm probably not going to care. My delta x is unknown, and my time, I don't know. I got a lot of unknowns, so I probably am just going to skip over to the y side, right, if I'm solving this problem organically. So I'd look at the acceleration in the y direction. That'll just be the cosine component of 0.42. My initial velocity in the y direction is also 0, also starting from rest. My final velocity is also unknown, but this is the less interesting unknown to us. Delta y now, delta y is interesting. If I want to get to the point where I will collide with particle A on its horizontal trajectory, that means that I need to get all the way up to the line that particle A is moving along. In my case, that's 31 meters, y equals 31. So that's going to be given, is the important part there. And then again, I don't know time. So as I mentioned, I'm not concerned with final velocities. I'm probably going to ignore them. With y, it looks like I have enough information here to solve for t, except that I don't know theta. Explain one more time why. Yeah, let's explain that more explicitly. It's a good question. So they give us this acceleration vector, and they give it off of the, they give us our angle theta off of the vertical. This is what they're asking us to solve for. So what that means is if I resolve this vector A into its components, the y component would be adjacent to the angle, and the x component is opposite. So in every other problem that we've done so far this semester, the x component has been cosine, the y component has been sine. We flip that here because they asked for the angle off the vertical. They'll very rarely ask for the angle off the vertical, but you should know how to do it, and so we have to do that here. All right, so as I was mentioning, sort of my problem solving approach here is to say I know the acceleration, the initial velocity, the delta y. I don't actually know the acceleration because I don't know the angle, but sort of taking a shot in the dark here. Let's relate those three quantities, and we know that the most trustworthy quantity, time, will link our x to our y, and in this case it'll also link our a to our b. So I'm going to flip the page to do this next set of equations. We have delta y is equal to v initial t plus a half at squared. Delta y we said is 31. Our initial velocity is 0, so this first term goes to 0. If I could get a 0. And then I have a half times my acceleration. My acceleration is 0.42 times the cosine of theta. And then I have time squared. On the x side, I'd have the same equation. Delta x is equal to initial velocity times time plus 1/2 at squared. Delta x now I don't know, so that will remain unknown here. First term again goes to 0. Now I have a half. The acceleration in the x side is 0.42 sine of theta. And then I have t squared. So I have these two equations here. You'll notice if I look at the second equation, I have three unknowns, delta x, theta, and time. If I have three unknowns, that means I need a system of three equations. Recall that I'd written down an equation, one more back, from particle A that relates delta x and time. And as I mentioned, since both of these particles are starting at x equals 0 and traveling to some x final here, that means that they have the same delta x. So our last equation is delta x equals 3t. Now that I have these three equations, it's just a matter of doing math here. And this is the tricky part of this problem, is that this math is a little complicated. The way that you choose to go about it is up to you. There are a few different solutions floating around. So that's a nice thing, is this isn't a bottlenecked math problem. Sometimes math problems bottleneck and you have to know like one specific trick to solve them, which is terrible problem writing in my opinion. But in this case, you have several different ways that you can proceed. The two tools that every solution I've seen has made use of these, I think, is that these two identities, tangent theta is equal to sine theta over cosine theta. And then the old trusty Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. The one substitution that you might want to make right off the bat is to substitute 3t for delta x on the left-hand side of equation 2, so that you can then just relate these two equations. So fully internalizing these, let me write down what they'll be once I make that substitution. So that red equation there for delta x will become 3t is equal to a half times 0.42 times sine of theta times t squared. And then I'll copy down my second equation. My second equation was 31 equals a half times 0.42 cosine of theta times t squared. Now there's two ways to solve this. I gave one solution in the discussion section, and that solution is to square both sides of both equations, add them together, and then solve a quadratic. I'm going to try for a different solution here. Let me think about it for just a sec. I don't think I necessarily Yeah, I'm gonna solve it that way again. So the way this is going to work is if we know that these equalities hold, if I know A equals B, and I know that C equals D, then I can say that, for instance, A plus C is equal to B plus D. I did something like this a few minutes ago to solve one of the problems. I can add the left sides and add the right sides, and that equality will remain true. What I'm going to do in this problem is I'm going to go a little bit to an even higher level, is I'm going to say I can square them. Now, why would I be doing that other than just like, why would I do something so complicated as to square these equations? Well, keep in mind that I want sine squared and cosine squared. Once I get sine squared and cosine squared, then I can get rid of theta that way. So using a Pythagorean identity, I can eliminate theta. So I'm going to square both sides of the equations and add the respective sides together. And that, am I going to have room to do that here? I think I actually need to do it on the next page. So I'm going to have 3t squared plus 31 squared will become the left-hand side of my equation. On the right-hand side, I'm going to have a whole bunch of junk. Whoops. I'm going to have a half times 0.42 sine theta t squared quantity squared plus a half times 0.42 cosine theta t squared quantity squared. Okay, let's write all that out. A half times 0.42 sine squared, or rather sine theta t squared quantity squared plus a half times 0.42 cosine theta t squared, and that whole quantity is also squared. Now what I'd like to do on the right-hand side is pull out all of the common stuff to these two terms. I also know, because I know I want to use sine squared plus cosine squared, I know I want to be left over with a sine squared and a cosine squared. So I'm going to pull out a half, 0.42, and t squared. So I have a half times 0.42 times t squared, keeping in mind that all that stuff still has to be squared. What I'm left with in the first term is I'm left with a sine theta that is still squared, or in other words, sine squared theta. In my second term, I'll be left with just a cosine that is also squared, and that's cosine squared theta. And here we can employ the Pythagorean identity and substitute this whole thing for 1. Once we do that, we have on the left-hand side 3t squared plus 31 squared. On the right-hand side, we have now just a half times 0.42 times t squared, this whole quantity squared. You may be tempted to like divide by t squared or something. Maybe we can cancel those out, but you'll see that on the left-hand side, although on the left-hand side we have a t squared, on the right-hand side we have a t squared squared. That's actually going to be t to the 4th. So what we need to do instead is group our terms together. So subtract these two terms from both sides. We'll have 0 is equal to the 1/2 times 0.42 times t squared quantity squared, or in other words, let's just go ahead and do this now. We can put, oops, that t squared will become t to the 4th. So let's go ahead and write that down. Our next term is we have minus 3t squared. If I expand that, that would be 9t squared. I'm doing this because I want to take a look directly at my t's, and then subtract 31 squared. Now, hopefully I have an equation, hopefully you're starting to get an idea of where I'm going here. This should look something like a quadratic where you have like some term ax squared plus bx plus c, and then you can plug it into the quadratic equation. I don't quite have that though because it's quartic. I have t to the fourth and t squared. So the last thing I need to do before I have a quadratic that I can solve is I need to do a quick substitution. So I can do something like, say, define some new variable alpha that's equal to t squared, and then just make that substitution. And now I'll have, let's see if I can remember it off the top of my head, 0 is equal to quantity 1/2 times 0.42 squared. This was t to the fourth, so now it's going to be alpha squared. And then I have minus 9 t squared is substituted out for alpha, and then minus 31 squared. Now we have a quadratic, which we know how to solve. You can do opposite of b plus or minus square root of a squared, opposite of b plus or minus a square root of b squared minus 4ac all over 2a. You can do that. You can plug it into a graphing calculator and find the zeros of the quadratic, however you'd like to do it. Ultimately, you'll solve for your alpha, whatever it is. Then you need to find t. In order to do that, you reverse this relationship up here. So t will be the square root of alpha. And then once you have your time, you can go ahead and plug it into one of your other equations. Ultimately, you're looking for the angle. So you'd want to choose from your set of equations here, you'd want to choose the equation that will directly give you the angle when you plug in the time. So probably this one. But I'll just go ahead and leave that. I'll say something like you then want to relate the time to theta, and theta will be your answer. If you need help with that, you can feel free to ask. I'm not going to give the entire explicit solution. If not, do we have any other questions on this?
I have one quick question for 5b.
For 5b. Okay, first, does anyone have any questions on this one before I'm... Okay, I'm not hearing or seeing. Okay, 5b. Yeah, let me hit the... I'm going to go ahead and stop the recording here.